All right, so welcome back. This is section 3.2. In section 3.2, we're going to take what we did in section 3.1, that is the graphing of those feasible regions, and we're actually going to do something with it. All right. So the title of the section is Solving Linear Programming Problems Graphically. Our objectives are to figure out what the heck linear programming is, so we're going to define it, and then we'll solve some linear programming problems graphically. So what is linear programming? All right, so linear programming is a process where a system of linear inequalities is used to represent the limitations of a given scenario. The feasible region then represents all the possible solutions to that scenario, and then one or possibly many of the solution points within that feasible region will optimize, by optimize meaning maximize or minimize, the given objective of the scenario. That was a lot that said very little. So basically what linear programming is you're going to have something, some objective that you want to either maximize or minimize. So you're going to have some sort of a function. But because we're doing linear programming, it's just going to be a linear function that you want to optimize. You want to find a maximum or a minimum value to it. Right? But your function has limitations. Those limitations are going to be represented by the other inequalities in the system. And so those limitations, those inequalities, give us a feasible region. Somewhere in the feasible region is going to be a point where your job, your given objective, is either going to be maximized or minimized, whatever it is you're looking for. And so we have to go into that system and find where that happens. All right, so you ready for the terminology? We're going to have constraints. Constraints are going to be all of those linear inequalities that limit the system. Now, in the best case scenario, they'll just be given to us. In the worst case, they'll be like that last problem we just looked at in 3.1, where we had to find all those inequalities. But those linear inequalities we're going to call our constraints. We're going to have the thing that we're going to call our objective function, and that is the thing that we wish to do. That is either the maximize or the minimize. Again, it'll be given to us sometimes, but often we'll have to solve for it. And then what's not usually written but is usually implied is that non-negative condition. Right? Since most of these should be word problems, then the variables in there don't make sense to be negative most of the time. And by most of the time, I mean just about every single time. And then the conditions then would be that the variables can't be negative, and so it's rarely ever stated, but it's often implied, and it gives us that non-negative condition. This is a really, really good thing, though, because this non-negative condition business down here, this is what usually forces us to only care about the first quadrant, which makes graphing these things a lot easier. Okay. All right, so let's take a look at an example. Happy Ice Cream Cone Company makes cake cones and sugar cones, both of which must be processed in the mixing department and in the baking department. Manufacturing one batch of cake cones requires 1 hour in the mixing department and 2 hours in the baking department, and producing one batch of sugar cones requires 2 hours in the mixing department and 1 hour in the baking department. Each department is operated for at most 12 hours per day, and each batch of cake cones earns a $47 profit, and the sugar cones earns a $63 profit. How many of each type should they produce to maximize profit? Okay. So I read through the problem, and I'm seeing all the points in there. Right? So let's take a look at what's being asked of us. Our job is to figure out how many of each type of cone should we produce to maximize profit. What that tells me is that my objective function is going to be all about profit, and I want to maximize it. But what are my limitations? Well, I have limitations because my mixing and baking departments cannot operate for more than 12 hours a day. So my constraints are I have limited hours in mixing and baking. And then, of course, where's the non-negative condition in here? Well, if the thing that I don't know is how many cake cones and sugar cones to make, then these represent my variables, and they can't be negative. Now this problem, actually, we could make an argument that it even goes one step further than that it just can't be negative. We could make an argument that since we're talking about batches of cake cones and batches of sugar cones, that not only can they not be negative, but they also must be integers, meaning I can't make 1.5 batches. I can only make a batch, or I can make 2 batches. Okay? All right, so now that I've got a basic idea of what's going on here, let's go over the process we're going to use, and then we'll come back to this problem and figure it out. Okay? The process is based on something called the corner point theorem. And the corner point theorem states that if an optimal value, that's the maximum or the minimum that we're looking for here, in this case the maximization of profit, if it exists, it's going to happen at one or more of the corner points of the feasible region. So when I draw this, and I'm just going to make a horrible sketch, and this is not to scale and this is not correct, but let's say that this ended up being my feasible region, some piece that looked like that had 1, 2, 3, 4 corners, and this was the feasible region, the inside of that. What the corner point theorem says is, if I call this one A, this one B, this one C, and this one D, that one of those corners is going to do the thing that I want to do, that's the maximization or the minimization, or, and here's the more of part of this definition, if both A and B maximize it, then the piece between A and B also maximizes it. So remember last chapter when we had to parameterize things? You'd have to parameterize on that edge. Now that doesn't happen. This is rare for that to happen. So don't get worried that that's going to happen a lot, okay? But it could happen, so we're going to put it out there. Usually what happens is one of the corners, A, B, C, or D, it does what you want it to do, maximizes or minimizes. That corner becomes your answer and you're done. Right? So here's how the process works. Number one, you read the problem and write the objective function and the constraints. Okay? 2, you graph that feasible region. 3, find your corners. 4, find the value of the objective function at each corner point. So find out how much the objective function is worth at A, at B, at C, at D. If there's more, do more. And then figure out which one does the thing you want it to do. Right? If your region happens to be bounded, and that's the best case scenario, then just look at which corner gives you that optimal value. If your region is unbounded, and down here on number 6, you want to check to make sure that a solution actually exists. Right? And what I mean by that is, if you had an unbounded region, and so let's say that you had something that looked like this time, a line coming down, another line like here, so that ends up being a corner, and the feasible region is everything going on forever out there, and you were looking for a maximum, you wouldn't find one. Because as you move out in that direction, your function could keep getting bigger and bigger and bigger and bigger and bigger, wouldn't have a max. Okay? Now, this again is another rare situation because it just rarely happens that the scenario would give you something that doesn't have an answer. Okay? All right, so I'm at 10 minutes right now, so let's take a look at a couple simple problems. When I say simple, I mean uncomplicated. Here what we have is someone has done the hard work for us. They've already graphed the feasible regions, right? The regions of feasible solutions. That's an older terminology. We mostly use feasible region now. Okay? And what we're supposed to do is we're supposed to use these regions to find the maximum and minimum of the given objective functions. And so I have two objective functions. I have z equals 3x plus 2y, and I have z equals x plus 4y. Now, I'm not sure why, but objective functions are almost always called z equals. Z equals this, z equals that. Okay? All right, so I'm going to start with this one as my objective function. I'm going to call this one corner A, this one corner B, this one corner C, and this one corner D. Okay? In corner A, what's the value of z? Well, z is 3 times x, so that'd be 3 times 3, plus 2 times y, so 2 times 8. So that's going to give me 9 plus 16, 25. And now I'll check corner B. What's the value of corner B? Well, z is equal to 3 times x, 3 times 7, plus 2 times y, 2 times 4, 21, plus 8, 29. Now I'll check corner C. Z is equal to 3 times x, plus 4 times y, 12 plus 4, 16. And now I'll check corner D. Z is equal to 3 times 0, plus 4 times 5, 4 times y, and I get 20. Okay? So at corner A, the objective function has a value of 25. At corner B, the objective function has a value of 29. At corner C, the objective function has a value of 16. And at corner D, the objective function has a value of 20. Now my job was to find the biggest and the smallest, and I think I've got that figured out. It looks like corner B will be our maximum, and it looks like corner C will be our minimum. Right? So then to wrap it up and make it look pretty, we would say that the objective function is maximized at the point 7, 4 with z equal to 29 and minimized at the point 4, 1, the corner, the point 4, 1 with z equal to 16. All right, so this is what we're going to do. We're going to graph a feasible region, find the corners, evaluate the corners in an objective function, and then do whatever it is we're supposed to do. Either maximize it or minimize it. This problem right here is just to learn how to do things. I cannot think of a scenario where you would find both the max and the min at the same time. Normally you would either just want the maximum or want the minimum. You wouldn't want both. Okay? All right, we're at like 13.5 minutes, so I'm going to stop this video here, come back, we'll pick up where we left off here. So I'll see you back here for part 2.